Hello. Hello and welcome to this video. In this video, we will study the 20th set of problems. Not 20th. Yeah, 20th set of problem. Problem number 191 to 200. But before we get started on that set, let me clarify the brain fade moment of last video. So it was question number 182. And this is the question 182. And when I looked at the solution, I said that it is incorrect. Calculation is incorrect, but actually the calculation was correct. The problem was here in xy would be 0 0, not 1995. Okay, because once x becomes 0 from here, y also becomes 0. Xt, it doesn't matter what is the value of t. Once x is 0, y is also 0. So with that out of the way, let's get started on question number 191. Okay. Question 191 says that the roots x1, x2 and x3 of the equation x cubed plus ax plus a is equal to 0, where a is real and a is not equal to 0. Satisfy x1 square by x2 plus x2 square by x3 plus x3 square by x1 is equal to minus 8. Then we have to find x1, x2 and x3. So we go to question 191. So we have Vieta solutions. So we plug in the root x1 plus x2 plus x3 is equal to 0. x1, x2 plus x2, x3 plus x3, x1 is equal to a, and x1, x2, x3 is equal to minus a. Also, because x1, x2, x3 are roots of this given equation, x cubed plus ax plus a is equal to 0, we will have x1 cube is equal to minus ax1 plus a, x2 cube is equal to minus x2 plus a, and x3 cube is equal to minus x3 plus a. Now, we don't have to prove that it is given that this equation is there, so we just calculate it by brute forcing and we arrive at this result. Okay, and from here we get that a is equal to minus 8. Okay, once we have that value, it is a simple matter of solving these various equations, and you will arrive at the roots as minus 2 and 1 plus minus square root of 5. Question 192 says that let p of x be a polynomial with the degree 2008 and leading coefficient 1 such that p of 0 is equal to 2007, p of 1 is equal to 2006, p of 2 is equal to 2005, and p of 2007 is equal to 0. Determine p of 2008. So we let a function of x such that f of x is equal to 2007 minus x. Then g of x is equal to p of x minus f of x is equal to x into x minus 1 into x minus 2 up to x minus 2007. Now we substitute the value of fx here, and we get p of x is equal to x into x minus 1 into x minus 2 up to x minus 2007 plus 2007 minus x. Once we have px, we can find out 2008. So if you put in 2008, it will be product of all these plus minus 1. Now we move on to question 193. It says if p of x denotes a polynomial of degree n such that p of k is equal to 1 by k, for k is equal to 1 to 3 up to n plus 1, then we have to find p of n plus 1. Now we have x p of x minus 1 is equal to k into x minus 1 into x minus 2 up to x minus n minus 1. Now we set x is equal to 0. Once we set x is equal to 0, k becomes minus 1 to the power n by n plus 1 factorial, which implies that n plus 2 p of n plus 2 minus 1 is equal to minus 1 to the power n, which implies that p of n plus 2 is equal to 1 plus minus 1 to the power n by n plus 2. So this should be n plus, this should be n plus 2 because we are given till n plus 1. So once we have solved that, we move on to question 194. This should be n plus 2. Yeah. Now question 194 says that if p of x denotes a polynomial of n such that p of k is equal to k by k plus 1 for k is equal to 1 to 3 up to n, find p of n plus 1. So we let q of x is equal to x plus 1 p of x minus x, which will be equal to k of x into x minus 1 into x minus 2 up to x minus n. We set x is equal to minus 1. We get k is equal to minus 1 to the power n plus 1 by n plus 1 factorial, which implies that q of n plus 1 is equal to minus 1 to the power n plus 1. So p of n plus 1 is n plus 1 plus minus 1 to the power n plus 1 by n plus 2. Question 195 says that let a, b, c denote three integers and let p denote a polynomial having all integral coefficients. Show that it is impossible that p of a is equal to b, p of b is equal to c, and p of c is equal to a. So since p is a polynomial with integral coefficients, therefore a minus b will divide p of a minus p of b. Now also b minus c will divide p of b minus p of b minus p of c. So clearly, when you divide, these remainders would be equal. So a minus b, b minus c, and c minus a must be equal in magnitude. Let's say that two of them, a minus b and b minus c, are equal. Once we have that, we can say that mod of a minus b plus mod of b minus c plus mod of c minus a is equal to mod of 2a minus b plus c minus a would be greater than equal to 2 of mod of a minus b minus mod of c minus a is equal to mod of a minus b, so that a is equal to b is equal to pa and c is equal to pb is equal to pa is equal to b. So abc will be equal. Question number 196. 196. We are given a polynomial and the coefficients of these powers of x, a1, a2, an minus 1 are non-negative, and it has n real roots. Prove that p of 2 is greater than or equal to 3 to the power n. So we will use a lemma to prove that. The lemma is if m lies between 0 and 1 and it is less than n, then 2 plus m into 2 plus n greater than or equal to 3 into 2 plus mn. So first we prove the lemma. We have 2 plus m into 2 plus n greater than or equal to 3 into 2 plus mn. Left hand side we evaluate 4 plus 2m plus 2n plus mn greater than or equal to 6 plus 3mn, which implies that 0 greater than or equal to 2 minus 2m minus 2n plus 2mn implies that 0 is greater than or equal to m minus 1 and n minus 1. So that is what our lemma is. Now we put alpha 1, alpha 2 up to alpha n in the polynomial p of x is equal to x minus alpha 1 into x minus alpha 2 up to x minus alpha n. Now we let beta I is equal to minus alpha I, then without loss of similarity we can assume that beta 1 less than beta 2 and so on up to beta n. Now you can see that from the given polynomial beta 1, beta 2 up to beta n, if you multiply it will be equal to 1. If beta n greater than or equal to 1, then beta 1, beta 2, beta n minus 1 when multiplied will be less than or equal to 1. Now p of 2 would be 2 plus beta 1 into 2 plus beta 2 up to 2 plus beta 2 to the power n. Now we repeat the lemma. Okay, this is what we had derived. So all these products, this should be 2. No, this is 3, fine. So we take the first 2 and we apply the lemma on that, so it becomes 3 into 3 plus beta 1 beta 2. Okay, and similarly we go on multiplying these, so we'll eventually land up 3 to the power n minus 1 into 2 plus beta 1 beta 2 into beta b. Now once we have that, it is greater than or equal to 3 to the power n from the lemma again. Now the other way to solve is that if beta 1, beta 2 and beta n are non-negative numbers, then by the MGM inequality, 2 plus beta I is equal to 1 plus 1 plus beta I greater than or equal to 3 cube root of beta I. And thus 2 plus beta 1, 2 plus beta 2 plus up to 2 plus beta to the power n is equal to 3 to the power n. And then we have, this should be, okay, cube root of beta 1, beta 2 and beta n. Okay, let me think. Okay, so you take these and you multiply. Yeah, that is correct. That is correct. So you see, the problem is very simple. If you choose the correct method, you don't have to do all this nonsense, and it's a very straightforward problem. So depending on technique, a problem can be very easy or can become very complicated. It is a matter of choosing correct term, correct technique. Now we move on to problem 197. It says that determine all the polynomials of degree n with each of its n plus 1 coefficients equal to plus minus 1 which have only real roots. So we let the polynomial to be n x to the power n plus n minus 1 x to the power n minus 1 up to a0, so that ai belongs in the set of 1 minus 1, and we let the roots be alpha I, where I varies from 1 to n. So without loss of generality, we can assume that n is equal to 1. So from Vieta's relationship, sigma alpha I would be equal to minus a n minus 1, sigma alpha I alpha j is equal to n minus 2, and so on. Now we compute sigma alpha I square, which would be equal to, there should be a square here. There should be a square. Sigma alpha I whole square minus 2 sigma alpha I alpha j, which gives us n minus 1 square, that is this squared, minus 2 n minus 2. Okay, now we have taken n is equal to 1. Okay, so all right, how this became 1? Okay, so this is 1, this is minus a minus 1. Okay, I'll clarify this, how this is 1. Okay, however, all the roots are real, therefore sigma a alpha is square greater than equal to 0, that is this would be greater than equal to 0. Okay, and hence n minus 1 is equal to minus 1. Okay, so from here we conclude that n minus 1 is minus 1, not really 1, so square would be 1. From here it has come. Okay, now this implies that sigma alpha I square is equal to 3. Okay, now we also have that sigma mod alpha I whole square, sorry, sigma mod of alpha I square is equal to sigma alpha I square is equal to 3, and product of all the mod of alphas is equal to mod of product of all alphas is equal to minus 1 to the power a0. We take mod of that, which would be equal to 1. Now once we have that, we use the root mean square and geometric mean inequality, and we arrive at this value, square root of 3 by n for product of mod of all alpha is raised to the power 1 by n. So once we have that, we can see that the maximum value of n is 3. So we find the equations as x minus 1, x plus 1, x square minus x plus 1, x square plus x minus 1, x cube minus x square minus x plus 1, x cube plus x square minus x minus 1, and their negatives are the equations which will satisfy this condition. Now we move on to question 198. If px be a polynomial over z and at least 3 distinct integers it takes, at 3 distinct integers it takes plus minus 1 value, prove that it has no integral roots. So without loss of generality, we assume that there are 3 integers abc for which the polynomial px will assume the value 1. Let d be one of its roots. So our polynomial p of d would be d minus a into d minus b into d minus c into some function q of x, for which it will become q of d plus 1. So for this root, we have this condition. Okay, so if you see what is the question? Okay, for at 3 distinct integers takes a value plus minus 1, so we assume it to be plus 1 here. Okay, where qx has integer coefficients, we know that for sure 1 of mod of d minus a, mod of d minus b, mod of d minus c is greater than 1. So P of d is equal to k q of d plus 1. That is q of d is equal to minus 1 by k. But d is an integer and q has integer coefficient, so we have a contradiction, and hence px cannot have integral root. Now we come to question 199. Let alpha beta be the roots of x square minus 6x plus 1 is equal to 0. Prove that alpha plus n, alpha to the power n plus beta to the power n is in set of z, where n is in the set of natural numbers. Prove that 5 does not divide alpha to the power n plus beta to the power n. So we have alpha plus beta is equal to 6, alpha beta is equal to 1 from here. Okay. So alpha to the power n into beta to the power n is equal to alpha plus beta into alpha to the power n minus 1 plus beta to the power n minus 1 minus alpha beta, alpha to the power n minus 2 plus beta to the power n minus 2, which is a recurrence relation and which will eventually come down to alpha plus beta and alpha beta, both of which are in z. And hence alpha n to the power beta to the power n belongs in z. And similarly, you can prove the second part of the equation that is left as an exercise. We come to the last problem of this set, problem number 200. Let p of x be a polynomial with real coefficients such that p of x greater than or equal to 0 for every real x. Prove that p of x is equal to f1x whole square, f2x whole square, up to p fn fx whole square. So we have to prove this, and we are given px with real coefficient, and px is greater than or equal to 0 for all real x. Now we are given that p of x greater than or equal to 0. If it has a root of odd multiplicity, then it changes sign at that root. So any real root must have even multiplicity. Okay. If x is equal to alpha plus I beta is a complex root, so is x is equal to alpha minus I beta, because the coefficients are real. Okay. Let xi be even number of real roots. There is a typing mistake. So p of x is equal to product of x minus xi whole square into product of x minus alpha j whole square plus beta j whole square. So these are the real roots, a number of even real roots, and then we have complex roots. Okay. So we now look at the product of complex roots, that would be equal to much, which will be equal to rx whole square plus ix whole square. And that's how we proceed to prove the problem. Okay. So with this, we come to the end of this video. I know that I went a bit fast, so you might have certain doubts that how this problem is solved and how the second part of this problem is solved. And you can have questions about this one also, 197. So if you have questions, then let me know in the comments. And do not forget to like the video, share it on social media, wherever you want, and make use of the comment box to ask questions. I'll be more than happy to answer it. If you have questions, maybe I can explain this in one of the next videos. I know that I have not explained everything, but this much should be enough for a student of reasonable intelligence to pick up and fill in the gaps in the solutions. So thanks a lot for watching. Enjoy.